So good day everyone. We are the group 1 and our group is tackled to discuss about this development of soil profiles. So next slide please. So first let's delve into the scopes of development of soil profiles. So first is the additions to soil and soil transformations. So we are going to discuss these two in the next further discussion. So next slide please. So first, let me tackle about development of profiles. So soil development occurs through several key processes that shape its composition and structure over time. So these processes include additions of new materials to the soil system, such as organic matter from decaying plants and animals, minerals particle from weathered rocks and other external inputs like dust or volcanic ash. So once these materials are introduced, they are undergo transformations within the soil, which involve chemical and biological changes that after these processes, for example, organic matter can decompose into simpler substances and minerals can break down or recombine to form new compounds. So in addition to transformations, there are transfers of materials within the soil profile. These transfers can occur both vertically and laterally. So as water moves these substances, such as clay, nutrients, and dissolved minerals downward, for example, leaching or upward through capillary action or gas release into the atmosphere, which can remove essential nutrients and other components from the soil. So together, these addition, transformation, transfers, and losses contribute to the continuous development and of evolution of soil over time. For example, this diagram illustrates the processes of soil transformation and composition changes, including addition, transformation, transfers, and losses. So first, additions. So inputs such as precipitations, including ions and solid particles, and organic matter are added to the soil from the surface. And then next one, transformation. Organic matter is transferred into humus and primary minerals undergo changes to form clays, hydrous oxide, and ions like silicic acid. So after that transfers, materials such as humus, compounds, clays, and ions like silicic acid are moved into within the soil. And then for losses, so some ions, including silicic acid, are lost from the soil system, likely through leaching or erosion. So this diagram actually depicts the dynamic nature of soil, but as a constant changing system, including the movement and transformation of organic and inorganic materials. So next reporter, please.
So next is the addition to soils. So the addition to soils is a direct inputs to the soil system, came from both outside and inside the ecosystem. The inputs from outside come from precipitation and wind, which deposits ions and dust particles, and floods and tidal exchange, which deposits sediments and solutes. The source of these materials determine their distribution and chemistry, leading to the distribution and leading to the development of soils with specific textural and chemical characteristics. Sometimes these inputs are huge. For example, hundreds to thousands grams per meter square of dust inputs to lowest accumulating regions of North America and Asia during the Pleistocene, and organic organisms within the ecosystem add organic matter and nitrogen to the soil as dead organic matter, including the above and below ground portions of plants and animals, and also soil microbes. So yeah. Next is the type of soil addition. Soil additions. There are two, again, organic amendments and inorganic amendments. So for organic amendments, there are three, which are the compost, green manures, and animal manures. And for the organic amendments, there are two classifications, calcium sources, for example, gypsum and biochar. So for organic amendments, again, there are three. First one is the compost, wherein it is derived from organic matter that has broken down, improves the structure of the soil, make nutrients more accessible, and stimulates microbe activity. It can also improve drainage in clayey soils and aid in moisture retention in sandy soils. Next is the green manure. With time, higher amounts of organic matter and improved soil fertility can be achieved by planting cover crops that are intended to be tilled back in the soil. And last classification is the animal manure, where when it is applied appropriately, farmyard manure and poultry litter, which are high in nutrients, can greatly increase the amount of organic matter. So next is the inorganic matter, rather inorganic amendments. Again, there are two, calcium sources and biochar. So for calcium sources, an example is gypsum, wherein the addition of calcium can strengthen microbial communities that maintain organic matter, control pH, and improve soil structure. And when it comes to enhancing drainage in clay soils without changing pH, gypsum is especially useful. Next classification is biochar. This is created by pyrolyzing organic matter and is a stable form of carbon that improves soil structure, retains nutrients better, and sequesters carbon. Next reporter, please.
So for the soil transformations, through the interaction of physical, chemical, biological processes, the materials within the soil are transferred. So in a process called of decomposition, the dead organic materials are transformed into soil by releasing the carbon dioxide and nutrients such as the nitrogen and phosphorus. Additionally, yung carbon content in soil is much more related doon sa clay content na nakakapag-affect doon sa soil kaysa doon sa mga climate effects. So what is weathering? Here you can see an example of a grow of a tree sa rock. So nakikita niyo dyan sa first GIF is yung nag-grow and nagkakaroon ng roots within the rock parts. So pwedeng mechanical processes or biological processes ito ng pag-grow ng root, which is nagkakause ng break doon sa rock. And yung second picture naman is yung pag-break ng isang one whole rock into pieces of rocks. So what is weathering? It is a process of changing the parent rocks and minerals to produce a more stable substance. This occurs when the physical and chemical condition of the surroundings and its composition changes from how they are formed. So there are two types of weathering, which is the physical and chemical. So focusing on the physical weathering, a very first example is yung pag-break ng isang rock, ang pag-break ng isang rock into two pieces from pag-break ng rock into two pieces ng dahil sa water. So later on, I will discuss on how this happened. So physical weathering. Physical weathering, it is a change of parent rock without chemical change and is formed through fragmentation. It can occur by expansion and contraction of rocks during freeze-thaw, heating, cooling, wetting, drying, or the break of rocks when the roots grow into rock features like our first example. So, nakita nyo dito sa picture is yung compaction or parang for the contraction of rocks. So, there are tiny pieces of rocks and after a long period of time, na-compact siya, layers of layers of soils has been compacting the rock into one, and kaya nag-turn ito ng one rock sa dulo. So, another example is when yung kapag may sunog. So, the fire causes heat on the outer layer of rocks while keeping the deep layers cool. So, mainit yung rock can causes yung pagbe-break ng rocks into smaller pieces. It can as well happen when the rocks are abraided by wind or ground against one another by glaciers, landslides, or floods. So next slide. So ito naman, this process allows rock to have an open channel for water and air penetration. So yung first GIF nakita niyo dyan, yung wind can cause the weathering by blowing grains of sand against a rock. So yung other naman is yung kapag umuulan naman, rain and waves causes weathering by slowly wearing rock away over a long period of time. So parang inaagos yung rocks away from its original place. So the second picture here is what I shown before. So here nakita nyo one whole rock siya. So malaking rock siya. And then yung second part nun is nag-break na siya into 1, 2, 3, 4, 5, 6, 7 yan. 7 na column of rocks. So water can get into cracks in a rock, and if it freezes, the ice will expand and push the cracks apart. Kaya yun yung nagiging force ng water down para mag-break yung rock into pieces. So when the ice melts, more water can get into the larger crack, and then mag-freeze siya ulit, kaya yun mag-expand ulit, and then magiging mas malaki yung break ng mas magiging malaki yung crack doon sa rock. Kaya after a very very long period of time, nakita niyo yung mga rock formation na yan, nagbe-break na siya dahil possible is one of the possible causes yung water.
Okay, so now let's move forward to chemical weathering. So it's the process by which parent rock materials react with acidic or oxidizing substances, typically in the presence of water, resulting in the dissolution of primary minerals and the formation of secondary minerals. So this occurs when the parent or the original rocks react with substances that cause chemical changes. The primary mineral dissolves and releases ions, forming new minerals called secondary minerals. Next. So these reactions include oxidation, hydrolysis, and carbonation. So this is the first oxidation is the reaction of rock minerals with oxygen, kaya nag-change yung mineral composition of the rock. When minerals in rock oxidize, they become less resistant to weathering. Iron, a commonly known mineral, becomes red or rust-colored when oxidized. Next. Hydrolysis is a chemical reaction caused by water. Water changes the chemical composition and size of minerals in rock, making them less resistant to weathering also. A hydrolysis reaction of alkali feldspar, a common mineral found in igneous rock, yields kaolinite, silicic acid, and potassium. Next. So carbonation. Carbonation is the process of rock minerals reacting with carbonic acid. Carbonic acid is formed when the water
combines with carbon dioxide. Carbonic acid dissolves or breaks down minerals in the rock. So yung role ng acidic substances and water, yung acidic substances, it accelerate the weathering process by increasing the acidity of the environment. Example, this is the most carbonic acid is the most important acids sa weathering, which is formed through reaction of carbon dioxide with water and then ionizes to produce a hydrogen ion and a bicarbonate ion. And then water naman, it acts as a solvent facilitating the dissolution of minerals. Next. So here are the importance of carbonic acid. First is it is a primary acid agent. Carbonic acid is the most significant acid in chemical weathering. It forms, as mentioned earlier, carbon dioxide reacts with water, creating a weak acid that can dissolve minerals. Next is it is an enhanced it enhanced carbon dioxide concentration. Higher carbon dioxide level in soil promotes carbonic acid formation. The concentration of this in soil is significantly higher than in the atmosphere due to respiration by plants, animals, and microbes, as well as the slow diffusion of gases in soil. Root zone activity. Biological activity near roots increases carbon dioxide and organic acid production, further increasing the concentration of carbonic acid and accelerating weathering in the rhizosphere. Mineral dissolution. Carbonic acid reacts with minerals leading to their dissolution and the formation of secondary minerals. So yung carbonic acid, it reacts with minerals like potassium, feldspar, breaking down the mineral structure and releasing soluble ions. This process contributes to the formation of secondary minerals like kaolinite. Next is the soil formation. It plays an important role in soil development as it releases essential nutrients and creates the necessary conditions for soil development. Lastly, for the importance is the global carbon cycle. It helps regulate the Earth's carbon cycle. So chemical weathering involving carbonic acid helps regulate the Earth's carbon cycle by removing carbon dioxide from the atmosphere and storing it in minerals. Next. So this is how secondary minerals are formed. So first is the dissolution of primary minerals. Acids react with primary minerals, breaking down their structure and releasing ions. For example, yung mga carbonic acid, organic acids, nitric acid, and sulfuric acid. And then magta-transport yung ions, yung released ions transported through water. The released ions are then transported through water, and then yun na yung precipitation of secondary minerals. So ions may precipitate out of solution under specific conditions, forming new minerals. These conditions, for example, changes in pH, temperature, or concentration, which may precipitate out of solution to form new minerals. So here are the factors affecting secondary mineral formation. First is yung climate, soil pH, vegetation, and yung parent rock composition. Next. Ayan. So, pabalik, sorry. Ayan. So, yung climate, warm, wet climates promote chemical weathering and therefore the formation ng secondary minerals nga. Yung soil pH naman, solubility of ions and the types of secondary minerals that will be formed. And yung vegetation naman, plants and microbes contribute to the production of organic acids, which also accelerates yung chemical weathering and yung formation din ng minerals, secondary minerals. And lastly, for this is the parent rock composition. So ito, presento, that will determine the composition of the secondary minerals formed. Next. So for temperature and climate, warm climates, wet conditions, humid tropics. So for warm climates, higher temperatures speed up chemical reactions. Higher temperature, so maglilid siya to faster weathering rates. What conditions? Abundant moisture promotes chemical reactions and biological activity. Humid tropics, the combination of high temperatures and rainfall in tropical regions creates ideal conditions for rapid chemical weathering. Next. This is the role of plants and microbes. Yung organic acid production, plants and microbes release organic acids into the soil, which contribute to acidity. Yung chelate. So next is this happens when organic acids bind to metal ions, making them soluble, which can disrupt a mineral equilibrium and accelerates weathering. And lastly, for this is yung high biological activity near roots na nagpo-produce ng carbon dioxide and organic acids. Next. So lastly is the effects of organic acid. So parang na-mention na rin ito kanina, but organic acids increase soil acidity, which directly attack minerals, and then it also dissolves certain minerals, releasing ions into soil solution, and increases the solubility of metal ions. Next reporter, please.
Thank you so much. So today I will walk you through the three major types of rocks: sedimentary, igneous, and metamorphic rocks. Let's explore each type and their key characteristics. Next slide, please. Yeah. So as you can see on the table, we'll be focusing much on the sedimentary rocks and the igneous rocks. So the sedimentary rocks, these rocks are formed through the accumulation of sediments. Basically, this is formed when different kinds of particles from different rocks combine together, which forms the sedimentary rocks. This often contains fossils, which is very important since this tells us more about the history of our life or the life of Earth. Next up would be the igneous rocks. Well, igneous rocks are formed when magma cools down and solidifies. Depending on how quickly they cool, they can be coarse grained or fine grained, such as basalt. Unlike sedimentary rocks, igneous rocks generally do not contain fossils since igneous rocks are formed through, just like what I said earlier, the cooling of magma, and magma rarely contains fossils. Just like what I said, there's also the metamorphic rocks, but we won't be focusing much on that. Next slide, please. So these are just some of the examples of the sedimentary rocks: the siltstone, the gypsum, and the limestone. Next slide, please. Okay, so for the igneous rocks, this would be the granite, the obsidian, and the basalt. These are just some. As you can see, there are two kinds of appearances. It could be coarse grained or fine grained. Fine grained, an example would be the obsidian in the middle, which is shiny or smooth. Next slide, please. So for minerals susceptible to weathering, there are certain factors that would affect this. So one, the physical and chemical properties of the minerals determine how quickly they weather and what byproducts they would provide. Minerals with weaker chemical bonds break down faster, of course, while those with stronger bonds tend to take time before it breaks down. Next would be the rock properties, the soil pH and nutrient supply. So soils formed through the sedimentary rocks have higher pH, which would be beneficial for the plant growth since they would have higher cation availability or nutrient availability. In contrast, igneous rocks lead to more acidic soils with fewer available nutrients, making them less fertile. The order of mineral weathering, for an example, olivine weathers the fastest because of its weak bonding. Feldspar takes longer to weather, while quartz is the most resistant due to its strong crystalline bonds. As you can see, or as you all know, quartz is like a crystal formed rock, meaning it has strong bonds with each other, which causes it to be less susceptible to weather. Next slide, please. Okay. So as the minerals weather, elements leach out and enter the rivers in predictable sequence. I took the example of rivers because most of the time rivers are moving, which causes weather. So the sequence would be chloride, sulfate, sodium, calcium, magnesium, potassium, silica, iron, then aluminum. Next slide, please. Now let's talk about the clay formation and its unique structure. Now, for clay formation, the clay minerals are insoluble products of chemical weathering. They consist of hydrated silicates containing elements like aluminum, iron, and magnesium. This formation occurs as other minerals break down over time, especially in the presence of water, just like the river earlier. So the structure of clay minerals are made up of two types of sheets that stack together. First, the tetrahedral sheet. The sheet has silicon atoms at the center, surrounded by four oxygen atoms, forming the tetrahedral shape. You can be seeing that on the figure A and B, wherein the B is the sheet. Next would be the octahedral sheet, as you can see on the figure C and D. In this layer, ions like aluminum, magnesium, or iron are surrounded by six oxygen or hydroxyl groups, creating an octahedral structure. Next slide, please. Okay. So let's talk about how secondary minerals influence soil properties, including water movement, nutrient exchange, and fertility. First, uh, conversion of primary to secondary minerals. Weathering converts primary minerals, just like sand, into secondary minerals, just like clay, increasing the proportion of small particles over time. Influence on soil texture. In areas with faster weathering, temperate and low tropical regions, soils tend to have higher clay content. Since in faster weathering, more clay are produced. And so, like what I said earlier, clay are produced when the insoluble products of some rocks are clumped together to form the clay. High latitude soils with slower weathering often have low clay content. Erosion and deposition effects. Weathering interacts with erosion and transport processes, redistributing fine particles, just like clay, to valleys, while coarser particles remain on slopes. Next slide, please. Mineral loss over time. Extended weathering leads to mineral dissolution and nutrient loss, affecting the soil fertility and structure. So, example, if there's a land that is very fertile originally, but then weathering was enhanced at that time, causing some of its properties to be washed away by the water, making it lose the minerals it contains. Impact on water holding capacity and nutrient retention. Since it's the same with the mineral loss over time. Uh, if there's too much weathering on that end, it would increase the soil's surface area, enhancing its ability to hold water and retain nutrients. Weathered soils with high clay content support better plant growth due to improved water and nutrient retention. Chemical changes and cation exchange capacity, or CEC. Weathering reduces the CEC of soil minerals over time, affecting the availability of essential cations for plant absorption. Organic matter can compensate for reduced CEC in highly weathered soils by providing additional nutrient binding capacity. Next slide, please. Okay. So for the role of allophane, so allophane is an amorphous or non-crystalline secondary mineral commonly found in volcanic ash deposits. Its structure makes it distinct from other minerals, giving it unique properties that influence soil chemistry. An example of allophane can be seen on the upper right corner of the screen. So the allophane transforms over time as it loses its silica, which gradually transforms it into more stable crystalline minerals such as gibbsite. This transformation marks a key change in soil mineralogy as volcanic soils mature. So the blue part of that rock is what we call the gibbsite. So the key functions of allophane. High anion exchange capacity, or AEC, has olefin has a surplus of positive charges, which allows it to efficiently absorb negatively charged ions or anions, like nitrate or phosphorus. It's like a magnet, negative attracts positive, and since olefin has too much positive charges, it absorbs the negative charges. Phosphorus binding, olefin binds with phosphorus since it has more positive charges, which limitation in young volcanic salts, reducing nutrient availability for plants. Now, for the long-term impact of the olefin, as olefin transforms into crystalline aluminum oxide minerals, it alters the mineral composition of the soil. This transformation affects both nutrient availability and soil structure, influencing how well the soil can support plant life as it matters. Next slide, please.
So for the overall summary of this report, so for the conclusion, the development of soil profiles is dynamic process shaped by the combination factors that interact over time. As mentioned earlier, this process involves four main stages: additions, transformation, transfers, and losses. So addition to soil occurs through inputs such as organic matter from decaying plants and animals, atmospheric dust, and mineral deposit. So these additions provide raw materials for that fuels the soil development, enhancing the fertility and structure of the soil. So soil transformation, particularly weathering processes, play a crucial role in the breakdown and alteration of these materials. So physical weathering breaks down rocks into smaller particles, increasing the surface area for further chemical changes. Meanwhile, chemical weathering, as mentioned earlier also, involves reactions such as oxidation, hydrolysis, and carbonation, which transfers primary minerals into secondary minerals, forming clay particles and releasing nutrients. So these transformations are important for creating soil horizons, distinct layers within the soil profile with varying compositions and textures. So transfers within the soil, such as movement of dissolved ions, clay, ignore organic matter results from water percolating from through the soil. That distribution of materials leads to horizon differentiation of some layers accumulating from more organic or clay, while others may experience leaching of nutrients. So, for losses, including erosions and leaching, further shapes the soil profile by removing materials from the system, which may lead to nutrient depletion over time. So together, these processes are very complex and ongoing cycle of soil development where the interaction between additions, transformation, transfers, and losses determines the characteristics of the soil and its suitability for supporting the overall plant life and other ecosystems. So that's all. Next slide. So thank you so much for listening, and this is the end of our report. Thank you.